So whenever you're given one of these sort of general regions, it very much helps to sketch the region that you're integrating over. Okay, so we'll draw vertices of the triangle. And now we care about this guy here. Yes, John?
Is that triangle considered a level curve, or does that have to be defined by a function to build?
Right, yeah, so this isn't, okay, this is the level curve of some function, but not this one. Right, this triangle is kind of independent of that function. I think it's helpful to just think of this as a triangle and not try and create a function to get level curves involved. Okay, so we've got this guy. Eventually we're going to need a way of parameterizing this hypotenuse here. Right, so we want to find an equation for that hypotenuse. So we've got 2 points on the line, and we could use grade 9 techniques to get the equation of that line. Okay, so now we'll set up the integral. Now to evaluate this, we have to pick some order to evaluate this thing in. So we're going to pick the order dx, dy. Arbitrary choice, we'll pick one order. Okay. Yes, Emily.
You just wrote that the function x, y is equals x times y?
Yeah, sorry, that should be a times. I got confused about what example I was in.
Yeah.
Okay. So with these questions, I really, really like this fill in the box approach to solving them. To write out your order of integration first, leave some big boxes that you can fill in, and then go step by step. Okay, so when we're filling out our order of integration or our bounds for integration, we work with the outside thing first. Okay, so what we need to determine is what values does y assume in this calculation? Okay, so we're going to be moving along different values of y. We'll start at y equals 0, go up a bit more, until we get to y equals 1. Okay, so in this order of integration, y runs from 0 to 1. just gonna make kind of a note. Start with the outermost integral. Y equals 0 to y equals 1. And now comes the very hard part. When we start off down here, x is allowed to run from 0 to 1. Then when we go up a little bit more, x has less room to move. Up a bit more, x has less room to move. All the way until x is just at that one point there. Okay, so the value of y determines the values that x can assume. So here, let's say y is a half. Right, so let's say we're right in the middle there. Now, we're at this point, but half is 1 minus x, so x is also a half. Okay. So when we go to y equals a half, x can only go up to a half. Yes?
How did you get to x, y equals 1 minus x? Is that just x squared minus y plus y squared equals 1?
Right, okay, oh, so you're saying where did that line come from?
Yeah.
Right, okay. Oh geez. Where should I write that? Okay, let's write that up top here. So here's our triangles, and what I want is a formula that tells me that hypotenuse. I want to know, given x, what is y, given y, what is x. Okay? So I've got 2 points on a line, so I'm going to use grade 9 techniques to find the slope. Right, so I'll say rise over run. Right, so I get that of slope -1. Now we'll solve for what b must be. So we'll put in this point here. Right, we'll put in one of the points. Right, so we've got the equation of that hypotenuse now. Did that help?
Yes.
That works? Nice. Nice. Okay, I want to take a moment and kind of just write this in a slightly more symmetric form. That's nice. Very symmetric. Okay, so we've got the equation of that line. We've got it very nice and symmetric looking. Now we need to figure out the bounds on x. Where can x go given a value of y? Okay, so notice that x always starts off here and runs to that hypotenuse. It starts off at x equals 0 until it gets to the hypotenuse of this triangle. Okay, so x starts off at 0. Okay, now coming back to the tricky, subtle, difficult point. So what are these x coordinates? So given a value of y, we can solve for x and get 1 minus y. Okay, so our upper bound there is 1 minus y. How do we check that that makes sense? That that is the right upper bound? Yes.
I guess when you're going to be integrating with respect to y, you'll have a function in terms of y there, which is what you want.
Yeah, that's really nice. Yes, 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 yes. When we integrate this dx, the final result will be a function of just y. And that's super good because this will integrate it and give us a number then. Yeah. Yeah, so you can check that the order of integration would have to work out correctly so that you don't have variables at the end. Nice. Yes. Any other thoughts that might help us check if that's right?
You just plug in the y value from your y integration and make sure that you get to the same point.
Yeah, great. So if I start off at y equals 0, at y equals 0, this thing runs from 0 to 1, right? Which seems pretty good. If I plug in a tenth, then I run from 0 to 9/10. That's pretty good. If I plug in a half, I run from 0 to a half. And if I plug in my top value here, y equals 1, I run from 0 to 0. Seems pretty legit. Okay. We cut this way. Okay, great. So now we've got the integral set up. So we shall integrate. Actually, wait. You know what? Let's stop there. Otherwise, we'll go like 5 minutes over. Okay. So we'll come back to this integral, and we'll come back to the notion of parameterizing regions.